Mid-February 1943, Sidi Bou Zid in Tunisia. The captured M4A1 Sherman came to a halt in the warm desert sand, its American star still faintly visible underneath the quickly applied German cross. Officers from the heavy Panzer Battalion 501 gathered around the tank with notebooks ready. This single American vehicle, taken intact and still fully functional after the fighting near Sidboid, would set off a moment of reflection among German engineers that would continue to influence their development work for the remainder of the conflict. The calculations of armored warfare were about to change, not because of stronger guns or thicker armor, but because of something the Germans had never placed at the center of their designs. It was mechanical reliability that refused to fail. The tank carried the name War Daddy 2 on its hull, marked with serial number USA 3067641. It had been manufactured by Limmer Locomotive Works and assigned to Company G of the 1st Armored Regiment in the 1st Armored Division. A German reconnaissance unit had driven this Sherman for 350 kilometers across the North African landscape to the port of Sfax, a journey that lasted 4.5 days. Each kilometer added evidence that challenged long-held German beliefs about American industrial practices. The engine remained steady, the transmission continued to function smoothly, and the final drives kept a consistent output. German tank crews, familiar with frequent stops for mechanical issues even on modest road marches, grew uneasy as this foreign tank completed its route without major complaints in conditions that would often halt their own machines. At the port, War Daddy 2 was placed on a cargo ship headed for Germany. The weapons office had given strict instructions that the tank must arrive at the test center in Kummersdorf in working condition. German intelligence had collected incomplete reports about American production, but standing in front of the actual vehicle made those figures far more concrete than any earlier briefings. The Sherman showed what large-scale manufacturing could achieve, built on automotive design principles that Germany had not fully embraced. While the ship moved north across the Mediterranean, engineers in the Wehrmacht prepared their testing plans, knowing these examinations would reveal lessons they had avoided, confronting about their own engineering limits and about the rapidly developing capabilities of their opponent. Spring 1943. Kummersdorf Proving Ground in Brandenburg, Germany. War Daddy 2 rolled down from the transport rail car, bearing the marking for Zugfahrts 259 and the German license plate WH05 8941. Test engineers had already applied armor thickness, notes, and angle measurements across the surface of the vehicle, setting the stage for a detailed evaluation. The Army Proving Ground at Kummersdorf, located about 25 kilometers south of Berlin, served as the central site for examining both German and captured Allied equipment. Here, engineers carried out careful measurements, tested mechanical systems, and reviewed everything from track tension to transmission efficiency, recording their findings in extensive technical reports. The Sherman was now entering the most complete automotive review the German engineers could perform. Teams of specialists from several technical branches conducted the first inspection. They photographed each component from many angles, took careful measurements of every clearance, and documented construction features that appeared unusually direct and uncomplicated when compared with German production methods. The transmission drew immediate interest from the powertrain team. German tanks typically relied on straight-cut gears that required strict tolerances and frequent adjustments, while the Sherman used herringbone-cut gears that spread mechanical stress across more than one tooth at a time. This design, widely used in American automotive manufacturing since the 1932, offered strong durability while demanding less precision during production. German engineers had long considered herringbone gears impractical for large-scale manufacturing based on their own industrial limits and workforce training. American factories, however, had been producing them in very large quantities. Testing began with standard automotive trials meant to challenge all major systems under controlled conditions. Engineers drove War Daddy through obstacle courses built to imitate battlefield terrain, tracking fuel use, watching engine temperatures, and noting transmission response under different loads. After each stage, they opened the components to inspect wear patterns, checking for stress indicators, lubrication issues, or weaknesses in design. The results contradicted long-standing assumptions within German tank doctrine about the balance between performance and reliability. The Sherman performed reasonably well in every measured area and excelled in the category German tanks often struggled with, which was extended operation without maintenance interruptions. The powertrain inspection highlighted major differences in engineering philosophy between the American and German approaches. The Sherman's transmission offered 5 forward gears and 1 reverse, with synchronized gears from 2nd through 5th. This removed the need for double clutching during regular operation, making the tank nearly as straightforward to drive as a civilian vehicle. German drivers, by comparison, spent significant time learning advanced double clutching and precise throttle control to prevent unnecessary wear on their transmissions. The Continental R975 radial engine installed in this Sherman showed strong tolerance for a wide range of conditions. Engineers noted that it maintained steady output in temperature environments that often caused German engines to overheat or lose efficiency. The cooling system, although simple, functioned with notable effectiveness. Its air filtration unit handled desert dust without the frequent blockages that created problems for German tanks in North Africa. Every system demonstrated a design approach that favored dependable function over complex optimization. June 6th and 7th, 1943, Hillis-Leen Artillery Range. Reich Minister Albert Speer arrived to oversee a major armament conference attended by leading industrial figures and senior officers of the Wehrmacht. The program included hill climbing tests that compared German and captured Allied tanks. War Daddy 2 was positioned beside the newest German vehicles, including a Panther Aus FD recently completed at the factory and a Ferdinand tank destroyer that represented the most advanced armored technology Germany had produced. Speer, who oversaw German armament output and reported directly to Hitler on production results, needed a clear understanding of what American factories were capable of and how German designs measured against foreign equipment. The demonstration would reveal conclusions neither Speer nor German engineers wished to admit. The Sherman moved up the test slope with steady progress, its manual transmission with 5 forward gears, synchronized from 2nd through 5th, shifting without hesitation. Its engine provided a constant flow of power. The driver operated the tank with certainty, showing the straightforward handling that later became widely associated with the Sherman. The Panther was next. Its Maybach HL 230 engine, rated at about 700 horsepower, allowed it to match the Sherman's climb, though only with noticeably more effort. The Ferdinand, weighing 65 tons and built with an advanced electric transmission, stalled partway up the slope. Speer observed as crews attempted to restart the vehicle, an uncomfortable incident that played out in front of many senior officers and industrial leaders. In his memoirs written years later, Speer discussed the Sherman's performance that he observed during his trip through Italy in October 1944. He stated that reports about its cross-country mobility had been very positive, with the tank climbing terrain German experts believed tanks could not reach. He credited this to the Sherman having a strong engine relative to its weight, giving it cross-country mobility on level surfaces that surpassed German tanks. The 26th Panzer Division had specifically noted this strength. These comments from the minister responsible for armaments carried considerable influence within the Wehrmacht. A public version of this assessment appeared in Das Reich newspaper on June 27, 1943. The article described the Sherman as one of the notable achievements of North American laboratories and as a praiseworthy product of the North American steel industry. It emphasized that the first qualities to stand out were mass production methods and the ability to meet the demanding expectations of the North American automobile sector. The article mentioned the gyro-stabilized gun as the first of its kind attempted anywhere, recognizing the American effort in this development. These public remarks, written carefully to avoid sounding pessimistic, still hid the growing concerns spreading through German engineering offices. American tanks were not only acceptable, they were built with engineering choices that favored long-term field use. At Kummersdorf, structured testing continued from summer into autumn of 1943. Engineers evaluated the Sherman's operational range with extended trials that pushed the tank to its limits. They recorded ranges beyond 2,000 kilometers before major servicing was required. which was roughly 4 times the distance early Panthers could reach under field conditions. They measured transmission efficiency that surpassed any German tank, with lower drivetrain power losses than those found in German systems. They noted the synchronized manual transmission that allowed smooth gear changes without the double clutching or precise engine speed adjustments required by German vehicles. The final drives provided another discovery that challenged long-held German design beliefs. Panther tanks used final drive systems carried over from the Tiger, a setup vulnerable to failures under heavy loads. These systems relied on straight-cut gears inside housings that struggled to handle the strain of a 45-ton vehicle. Mechanics in North Africa and on the Eastern Front had reported recurring final drive problems, which often led to Panthers being left behind after short marches, sometimes under 100 kilometers. The Sherman's final drives, based on the same herringbone gear principles used in its transmission, rarely failed, even during extended operations that would often damage German components. The numbers presented a clear picture of the differences in reliability. Panther operational readiness averaged below 40% through much of 1943, with some units reporting severe rates as low as 20 to 25%. Certain Panther battalions recorded stretches in which fewer than 1 in 5 tanks were available for combat. In contrast, Sherman tanks consistently maintained much higher operational availability in every theatre. German field reports provided detailed records of Panther reliability issues. In July 1943, during Operation Citadel at Kursk, Panthers reached only 16% readiness, with mechanical failures disabling more tanks than combat losses. By December 1943, readiness had risen only to 37%. February 1944, reports again listed 37%. April 1944 reached 50%. May 1944 recorded 78%. These numbers represented the percentage of Panthers ready for combat on any given day, with the rest awaiting repairs or spare parts. The trend showed gradual progress as engineers corrected design flaws, but even at its best, the Panther never matched the readiness levels Shermans had achieved from the beginning. By December 1943, the conclusion was clear to anyone reviewing the data. The service life of the Sherman diesel engine exceeded 3,000 kilometers when maintained properly. Panther engines, even after improvements were introduced, rarely reached 1,000 kilometers. German records from March 1944 stated that upgraded Panther engines reached 700 to 1,000 kilometers and described this as an achievement. This performance still placed Panther engine life at roughly 1/3 of a Sherman diesel engine. Sherman transmissions required little attention between overhauls, with synchronized gears that reduced the chance of driver error causing damage. Panther transmissions needed constant oversight and frequent repair, with third gear failures so common that drivers avoided using it and shifted from second directly to fourth. Sherman final drives performed reliably, even in conditions that often destroyed Panther final drives after only 100 to 200 kilometers. German field reports from units that operated captured Shermans confirmed the Kummersdorf results with first-hand experience. Mechanized units short of dependable vehicles made use of any serviceable American tanks they could capture. Unlike Soviet T-34 tanks, which the Germans often rebuilt before using, Shermans entered German service without modification. They required none because they functioned correctly as produced, with no core mechanical faults that needed correction. German crews who had dealt with repeated failures in their own tanks found the Sherman's dependability noteworthy and mentioned it often in reports and letters. Notes from Panzer regiments described how Sherman crews could focus on tactics and combat, while Panther and Tiger crews worried about breakdowns before reaching the front or failing to return after a mission. The 10th SS Panzer Division captured 12 M4A 3 Shermans at Hellesheim in January 1945 during Operation Nordwind. These tanks came from the American 43rd Tank Battalion and were taken intact when their crews left them during the German attack. The 12 Shermans were organized into the 13th Company of the 10th SS Panzer Regiment and took part in combat for the remainder of the conflict. They served as reconnaissance vehicles and mobile reserves, roles that required steady movement and dependable mechanical performance. German commanders noted what the Kummersdorf tests had already shown. American tanks could be counted on to operate when needed. In the final months of the war, this reliability mattered more than gun power or armor. A Sherman that reached the battlefield with its main gun working was far more useful than a Panther with superior firepower that had stopped 20 kilometers behind the lines. January 1944 saw expanded testing as the Wehrmacht withdrew on several fronts, and more captured tanks arrived at Kummersdorf. Engineers examined the M4A1 with the Continental R975 radial engine, recording its features and comparing it with other models. They evaluated the M4A2 with its twin General Motors 6046 diesel engines, noting better fuel economy and different operating behavior. They studied the M4A3 with the Ford GAA V8 gasoline engine, a power plant many American crews preferred. All variants demonstrated the same key feature: strong automotive reliability supported by solid engineering and consistent manufacturing quality. The consistency among the different variants impressed German engineers, who were used to large quality differences between manufacturers producing vehicles that were supposed to be identical. The diesel-powered M4A2 made an especially strong impression on the teams who examined it at Kummersdorf. Soviet forces received 4,100 of these tanks through Lend-Lease, and many were captured during German advances and withdrawals on the Eastern Front. The twin GM6046 diesel engine delivered performance equal to any other Sherman model, while using much less fuel than gasoline engines, an important advantage as German fuel supplies declined sharply. German designers had previously tested diesel engines for armored vehicles, but abandoned the effort due to production difficulties and the complexity of fuel injection systems. American factories, however, produced diesel and gasoline Shermans side by side without slowing output, showing a level of manufacturing flexibility and technical capability that German industry never reached under wartime pressure. March 1944 brought reports from General Heinz Guderian, Inspector General of Panzer Troops, who stated in official documents that improvements in Panther reliability had finally reached what he considered acceptable standards by early 1944. Engine life had increased to between 700 and 1,000 kilometers, and many final drive problems had been reduced through design changes and better manufacturing. Although this was presented as a major accomplishment, it only brought Panther reliability to the level the Sherman had already achieved when production began in 1942. The Army was celebrating reaching a standard American tanks had surpassed from their earliest days, revealing how far German armored development had fallen behind. The comparison became even more difficult for Germany, as tank production was strained by resource shortages and continued Allied bombing. Strategic bombing focused on the most vulnerable points in the Panther and Tiger production process. The Maybach engine plant in Friedrichshafen suffered heavy damage during a Royal Air Force Bomber Command raid on the night of April 27th to 28th, 1944. The attack, involving 322 aircraft, is described in Imperial War Museum records as the most damaging blow to German tank production during the war. The raid also destroyed the ZF gearbox factory next to the engine facility. Tank engine and transmission production stopped completely for 6 months. When manufacturing resumed in November 1944, quality had declined. Forced labor, used in increasing numbers as German workers were drafted, carried out acts of sabotage. Cigarette filters were left in oil passages, gaskets were fitted incorrectly, and components were assembled without the required clearances. None of these problems affected Sherman manufacturing, which took place safely in American plants far from any battlefield and staffed by skilled workers earning reliable wages under stable conditions. The main difference between German and American tank production came not from engineering skill, but from industrial strength and design priorities. German engineers understood automotive principles as well as their American counterparts and possessed significant scientific expertise. They simply did not apply these principles consistently in tank design, choosing instead to emphasize other performance requirements. German tanks highlighted features that produced impressive specifications, but poor reliability under real field conditions. The Panther's 75mm KWK-42 gun and thick frontal armor placed heavy demands on a powertrain that struggled to carry a 45-ton vehicle. The Tiger's strong combat potential required complex maintenance and frequent repairs by experienced technicians. These trade-offs might have been manageable if German industry could build enough vehicles and spare parts to support them. It could not, especially as bombing increased and raw materials became harder to obtain. American engineers, shaped by decades of experience in large-scale automotive manufacturing, created tanks that could be built in very high numbers and maintained by mechanics with basic training drawn from civilian life. The Sherman powertrain used components that had already proved dependable in commercial use, supported by design ideas taken directly from automobile and truck manufacturing. Its electrical system included a backup generator capable of powering turret traverse, even when the engine stopped. To German designers, this seemed unnecessary, but in combat, it became a valuable advantage. German crews could only imagine such features, especially those who experienced turret systems that failed when engines stalled on uneven ground. These features did not appear in German technical documents, because German designers had never treated them as priorities when compared with armor and gun performance. By spring 1944, units across all fronts reported increasing mechanical difficulties as production quality declined and spare parts became harder to obtain. Panthers often needed to be transported by rail for any movement over 100 kilometers because their final drives could not endure extended road travel. Field commands issued specific instructions limiting Panther movement in order to preserve the tanks for combat rather than losing them to mechanical failure during marches. The Buffel Panther recovery vehicle, built on the same chassis and intended to retrieve disabled Panthers, suffered from the same reliability issues as the tanks it was meant to support. German commanders saw that mechanical problems removed more tanks from service than enemy action, with some formations noting that up to 70% of losses came from breakdowns rather than combat damage. At the same time, Sherman production increased at a scale German factories could not approach. American industry built 49,324 Shermans, more than the total number of German tanks of all types. Thousands were supplied to British Commonwealth forces, and the Soviet Union received more than 4,000 diesel models. Chinese forces in Burma used Shermans with notable success against Japanese armor that was less advanced than either American or German designs. Every region where Shermans operated confirmed the findings from Kummersdorf. Well maintained, Shermans continued running under conditions that would damage or disable German armored vehicles. German crews who captured and used Shermans consistently praised their mechanical reliability in letters, reports, and later interviews. Reports from the Eastern Front noted that German mechanics found even the complex Chrysler a 57 multibank engine made up of 5 separate engine blocks easier to service than German engines that required specialized tools and training. The Ford GAA 58, respected by Allied crews for its dependability and power output, impressed German mechanics accustomed to Maybach engines that needed frequent adjustment of valve settings, ignition systems, and carburetors. The General Motors twin diesel, considered less desirable by the US Army and assigned largely to Lend-Lease, still performed far better than any diesel engine German factories produced for tanks. The Sherman's broad design margins offered another lesson German engineers came to recognize. The transmission and final drive, originally designed for a 30-ton M4 with 400 horsepower, operated effectively on the 42-ton M4 A3E2 Jumbo, which carried significantly thicker armor. The same drivetrain that served the standard Sherman was capable of handling 650 horsepower from experimental engines without structural changes or reinforcement. German engineers often viewed such extra capacity as wasteful because it added cost and used scarce resources without providing immediate gains. American engineers understood that design margins allowed for future improvements and contributed to long-term battlefield reliability, making the added investment worthwhile. By summer 1944, German tank commanders confronting the Allied invasion in Normandy recognized that their disadvantages extended far beyond the technical features of individual tanks. American artillery, close air support, and logistical strength combined to overwhelm German forces regardless of tank specifications or battlefield skill. The Sherman's reliability meant American armored units could maintain consistent operations that German panzer divisions could not match. American tank battalions could attack, sustain action, pursue retreating forces, and prepare for the next mission without long maintenance delays. German formations had to conserve their limited number of functioning vehicles, knowing each movement reduced remaining mechanical life and increased the risk of breakdown. Differences in operational readiness decided which army could keep pressure on the enemy and which had to carefully allocate its remaining strength. German use of captured Shermans provided final evidence from the German viewpoint of American mechanical superiority. The 150th Panzer Brigade, created for infiltration missions during the Battle of the Bulge in December 1944, attempted to obtain captured American vehicles for disguise. Planners wanted Shermans in particular because of their reputation for reliability. The brigade obtained only 2 Shermans, and only one was in suitable condition for operations. The operational Sherman never reached combat because heavy traffic prevented the infiltration effort from meeting its goals. In a mission that required vehicles to operate continuously behind enemy lines with no support, only American equipment offered realistic chances of success. German tanks, even when working properly, could not guarantee the sustained performance such missions demanded. January 23, 1945, marked the final official recognition of Germany's automotive failure. A meeting of the Panzer Commission produced a report describing widespread final drive breakdowns across every major German tank type. The findings were severe. Before the 1945 Eastern Offensive, there were 500 defective final drives in the Panzer IV, 370 inches the Panther, and around 100 inches the Tiger. About 200 failures were also recorded in the Hetzer tank destroyer, built on the Czech 38-ton chassis. General Wolfgang Thomale, General Lieutenant and Chief of Staff to the Inspector General of Panzer Troops under Guderian, explained the operational results in direct terms. He wrote that in such circumstances, orderly use of tanks was impossible. Crews lost trust in their vehicles and at times abandoned entire tanks simply because of final drive issues, fearing they would be left behind and captured. German tanks, created to impress through outstanding technical specifications, failed at the most basic requirement of armored vehicles. They could not provide dependable mechanical performance to reach the battlefield and complete assigned missions. As Soviet forces pushed toward Berlin, the Kummersdorf testing center prepared for evacuation in early 1945. Engineers quickly packed records and shipped technical documents to locations farther west, hoping to preserve useful material for post-war study. Some of the captured tanks, including at least 2 Shermans, were put into improvised service by combat units defending the approaches to Berlin. These tanks operated beside German models in the final battles, offering one last comparison under combat conditions. The Shermans remained in action until they were destroyed by enemy fire or abandoned when fuel ran out. German tanks, including Panthers and the few surviving Tigers, continued to break down from mechanical issues at rates that surprised even veterans familiar with chronic reliability problems. The experience of War Daddy II and the many Shermans tested at Kummersdorf stands as one of the clearest examples of industrial imbalance in World War II. German engineers, working in a system that valued theoretical precision over practical effectiveness, created tanks that looked formidable in specifications but failed in extended field service. American engineers, applying long experience from the automobile industry, built tanks that lacked refinement in some areas but functioned dependably in conditions that routinely stopped German vehicles. In armored warfare, as in all military operations, the equipment that works reliably at the moment of need is more valuable than equipment that appears superior on paper but cannot complete its mission. Post-war investigations by American and British intelligence confirmed the results documented at Kummersdorf. Detailed study of destroyed German tanks showed mechanical failures to be as common as combat hits. Inspectors found broken final drives caused by stress, seized transmissions from poor lubrication or operator mistakes, and engines ruined by overheating or oil shortages. The German focus on individual technical superiority and impressive specifications had obscured the essential importance of reliability and serviceability. They produced tanks that conscript mechanics could not maintain without advanced training, powered by engines that required constant expert attention, supported by a logistics network that collapsed under the burden of supplying many unique parts for scattered units. The lessons learned from Kummersdorf shaped the approach to tank design in the post-war Bundeswehr of West Germany. When the Federal Republic began the development of the Leopard 1 main battle tank in the 1952, designers deliberately emphasized reliability and ease of maintenance instead of maximizing performance figures. They studied American automotive engineering practices and applied them directly to military vehicle design. The Leopard 1 incorporated many of the same principles that had made the Sherman successful. It used a strong powertrain with generous design margins, allowed quick maintenance with few specialized tools, relied on standardized components for fast repairs in the field, and offered room for growth without major redesign. The Leopard 1 went on to become one of the most successful tank designs of the Cold War, serving with many nations and remaining in production for years. The captured Shermans at Kummersdorf, including War Daddy 2 with its recognizable name still visible on the hull, represented far more than enemy vehicles brought back for inspection. They stood as clear evidence that mature industrial capability and practical engineering principles were more important than theoretical innovation, developed without considering manufacturing limits. German designers pursued advanced specifications because they believed superior technology could offset shortages in materials and the reality of being outnumbered. They were mistaken. American designers built dependable vehicles because they knew from long experience that logistics, maintenance, and steady operational readiness ultimately determined success in modern mechanized warfare. They were correct, and their approach proved decisive. The reliability gap between the Sherman and German tanks influenced not only battlefield tactics, but also shaped broader understanding of military-industrial power and its central role in modern conflict. Germany entered the war with technical advantages in many areas, supported by extensive scientific knowledge and strong engineering traditions. But Germany lacked the industrial capacity and manufacturing sophistication needed to sustain those advantages through mass production while fighting on several fronts. The United States entered the war with equipment that was often less refined, yet possessed an industrial base capable of producing overwhelming quantities of weapons, while continuously improving reliability and performance based on real combat experience. This industrial strategy, demonstrated clearly in the design and production of the Sherman, proved far more effective than German emphasis on technical refinement applied to small production runs. The United States built nearly as many Shermans as Germany produced tanks of all types combined, while also producing vast quantities of aircraft, ships, artillery, and other equipment, supporting allies through lend, lease, and maintaining a strong civilian economy. This economic strength, beyond Germany's reach even before bombing intensified, shaped the outcome of the war as surely as any battlefield victory. The comparison was straightforward when viewed objectively. A Sherman, armed with a 75mm gun that reached the battlefield and performed reliably, was far more valuable than a Panther with a superior gun that failed before engaging the enemy, or required days of maintenance for every day of crusade operation. A battalion with 80% of its tanks operational could execute missions that a battalion with only 40% readiness could not consider. Reliability was not a minor feature. It formed the basis of operational strength, determining whether armored units could carry out their assigned tasks. German tanks repeatedly failed this essential requirement. American tanks repeatedly met it. Kummersdorf testing had shown this clearly by mid-1943, even as German commanders continued to field Panthers and Tigers that looked formidable and carried impressive specifications but could not be trusted to operate when needed. The Sherman did not win the war through superior armor or firepower. It won through industrial strength expressed in mechanical reliability, steady availability, and ease of maintenance. German engineers at Kummersdorf understood this by mid-1943 through the detailed testing they conducted. They prepared reports describing their findings. They checked their results repeatedly with careful methods. They arrived at the correct conclusions about American advantages, but recognizing a problem and fixing it are not the same thing. German industry lacked the ability to reorganize production around reliability, while fighting a war against opponents with greater resources on multiple fronts. American industry had built reliability into its automobile manufacturing over decades of competition, and carried those lessons into military production with strong results. War Daddy 2, the Sherman captured in Tunisia and tested thoroughly at Kummersdorf, demonstrated the entire story through its dependable performance. Each kilometer it completed, without mechanical trouble, showed that German design had followed the wrong priorities by focusing on specifications instead of reliability. Each test that confirmed American automotive skill showed that industrial maturity and practical manufacturing experience mattered more than ambitious performance targets. Each comparison between Sherman and German tank reliability showed that Americans had addressed problems German designers had not fully recognized. The tank itself was ordinary in many respects, one among 49,000 produced, but what it revealed was deeply unsettling for German planners. It proved that Germany had already lost the industrial war even while fighting continued, and that American production capacity could not be matched regardless of German engineering ability or battlefield skill.